So asking here, we're going to ask for the number of H NMR and proton NMR and C13 NMR signals in each of these. So how many peaks, how many unique hydrogens, how many unique carbons. So the first thing I would do is draw in the hydrogens. For that first one. So another thing you should notice here, hopefully, is some symmetry, right? Some symmetry. Start looking for symmetry. Like a molecule that can be divided in half, that has some sort of plane of symmetry. So in this case, this molecule has a plane of symmetry. So that's going to mean it's going to have less proton signals and less carbon signals than you normally expect, right? Because it's symmetrical, it's going to have less peaks, less signals. So how many different types of hydrogens does it have? Yep, I would say 1. These are the same, so we label these A. These would be the same. Actually, these are all the same. It only has 2 types of hydrogen, not 3. Really symmetrical, right? So the splitting here, right? So this is another thing to get. So B, how many nearest neighbors does B have? That are 3 bonds away. We just did 3 bonds away. 1, 2, 3, but that's B. That's you can't couple to yourself. 1, 2, 3, and then 4. Maybe it hears A. A is 4 bonds away. Maybe it hears A, but I would predict B would probably be a singlet or maybe a doublet. Maybe. Right? How many hydrogens is B worth? 4. How many hydrogens is A worth? 6. Right? And we predict, if we just did a 3 bonds away, we predict they both be singlets. Now let's redraw it and look at, so for proton NMR, we have 2. Now for carbon, how many peaks would we have? For carbon NMR, how many peaks would we have? 3. 1. Each of the methyls is 1. So if I circle it in blue. Methyl, that's 1. Call that A. These guys, these carbons. And then the one I missed, I should take that away. So if I said this carbon and this carbon and this carbon and this carbon, they're all B. Then don't forget the carbons that don't have hydrogens bonded to them. That's usually the ones people forget in carbon 13 NMR. The carbon, even if you don't have hydrogens bonded to it, you're still a carbon, so you're still unique. So that would have 3 in the C13 NMR. And so don't forget the carbons that don't have any hydrogens bonded to them. All right, taking a look at this alkene. Oops. This alkene, so I went ahead and drew all the hydrogens in. How many unique hydrogens are in this one? I see 1. These are the same, those 2 methyls. 2, 3, 4, it's a D, not a B. And then this hydrogen, E, is different than this hydrogen, F. That can be kind of tricky to see, but remember, this H is trans to D. So it's a different position than E, right? Can we rotate about double bonds? No. So F and E are different because E is, you can say E is cis to D, F is trans to D, so they're different. So for proton NMR, I would predict 6 for HNMR. I'm going to redraw it again, see if we can find that number for C13. All right, for C13, I see 1, 2, 3, 4, and then both of these are the same, 5. See 5 different for C13. So what does this tell you? Is there some easy way to remember if there's more there's always be more carbons and hydrogens? No. So there's no way that you just got to think about the symmetry of the molecule and the different types of hydrogens or carbons. Right. All right, 4 different alkenes, same deal here. How many proton NMR signals? How many carbon NMR signals? So let's focus on the first one. What do we got for number of protons? Let's draw in those hydrogens. Again, we're looking for that symmetry. If you see a molecule that's symmetrical, and you got to realize there's going to be less signals than you'd expect. So this has some symmetry to it. How many different types of hydrogen does it have? Just 2. Just the 2. All right. A. And then both of these are the same. Because if you split the molecule, right, you can kind of divide the molecule in half either way. So I have two signals for HNMR. How many signals would you expect for C13 NMR? 3. 1, 2, 3, right? Don't forget the carbon that doesn't have any hydrogens bonded to it, right? Don't forget the quaternary carbons. Carbons without any hydrogens bonded to it are still things too. We'd predict there'd be 3 peaks in the carbon NMR. Well, this one, how many different peaks in the proton NMR? 4. Good, right? Just by all of a sudden, right, you think, oh, man, this is symmetrical. It's not, though, right? Once you just put that little hydrogen there, it makes it so it's not symmetrical. So 1, 2, 3, 4. Everybody see why these 2 methyls are different? This methyl is cis to that H. This methyl is trans to it, right? So that little stuff matters. So we predict there to be 4 for the HNMR. How many for the carbon? I would say 1, 2, 3, 4, 5. Excellent. 5 for the C13 NMR. Well, the next one. So I drew the hydrogens in here. How many different types of hydrogens does this molecule have? 2. Right? So see, there's symmetry now all of a sudden again. Now, if this was an ethyl, it wouldn't be symmetrical anymore, would it? Then it'd be all done. Right, but see how there's symmetry here? These 2 H's are actually the same. And these 2 methyls are actually the same. So 2 in the HNMR. How many in the carbon NMR?
2.
Careful. Is this carbon different than this carbon? They're the same. So there's just 2. 1 and 2. Either side is exactly the same. 2 in the C13 NMR. Last but not least, how many different types of hydrogens in this next one?
1.
Just the 1, right? All those methyls are the same. How many different types of carbon? 2. All right, you got the one that doesn't have any carbons bonded to it. Each of those are the same, and then all these methyls are exactly the same because of symmetry either way. So let's take a look at this alkene that we looked at before. So the number of peaks is going to be what? We said, let's call this one A, B, C, D, E, and F, and F. Okay? So let's break down the splitting and we'll worry about the frequencies later. We'll talk about that. You guys should be looking at your tables, but let's worry about the splitting first and how many hydrogens it represents. So for A, let's move left to right. A. How many nearest neighbors does A have? Who can A hear? You can hear who? This A. This A, yeah. This A, my A, can hear 1, 2, 3. It can hear C. 1, 2, 3, 4. It probably can't hear D. And it actually does hear B, guys. So just because it's on an alkene, and alkene's a special spot, 2 bonds away, it's going to hear it. So on alkenes, on these terminal alkenes, they're going to hear each other. It's the one time 2 bonds away they're going to hear each other. So A is going to hear both C and B. So A, what's C going to do to A? It's going to turn A into a doublet. And what's B going to do to A? Turn it into a doublet. And you can even put like a little, if you want to, like a little subscript so you know who's talking to who. Right? That's the doublet. The C and B are both talking to A. But now let's go to B. Who's B going to hear? B is going to hear, right? C, so it's going to be a doublet. And it's also going to hear A, so it's going to be a doublet. A doublet of doublets.
Can you explain?
Right, so if you're thinking about A here, A, who can A hear? Like I always think about songs. Right? They're like little bells, right? We're actually using radio frequencies, right? NMR. A can hear C. A can also hear B. B and C are different. So they're going to split or couple to A differently. So in one sense, A is going to couple to C, and that's going to turn into a doublet. But at the same time, A is also going to hear B, and B is also going to turn A into a doublet. But both those things are happening at the same time. So we call that a doublet of doublets. And you can hear multiple songs, right? You can hear 3 songs. You could be a doublet of doublets. You could be a doublet of triplets of all those kind of, you get crazy things happening. A lot of times you won't see it because you're not enough resolution to see it, but we're just kind of predicting what it could look like in a perfect scenario. All right, so B can hear A, and B can hear C. So B gets turned into a doublet by C, and also gets turned into a doublet by A. So it's a doublet of doublets. Now let's take a look at C. Well, who can C hear? 1, 2, 3. 1, 2, 3. 1, 2, 3. Whoa. C can hear 3 different songs. So let's do one at a time. So C hears A. What's A going to do to C? Doublet because of A. What's B going to do to C? Doublet because of B. What's D going to do to C? Triplet. All right, so I've denoted little subscripts with who's talking to who. Doublet of triplets.
So then it wouldn't be like a quintuplet or whatever.
So it might look like a quintuplet though, right? Mm-hmm. This is if the perfect scenario, if we had full resolution, you'd see it like this, right? It might end up looking like a quintuplet. But really it's a doublet of triplets. Because they're all different. It should hear 3 different songs. Now what it looks like in reality and an actual NMR, right? It might just be right, a quintet. But it really is a doublet of triplets. So it should have 3 different coupling constants, right? Because again, coupled by 3 different things. All right. Now let's go to D. Who can D hear? Can D hear 1, 2, 3, 4? It can't hear A. Or if we're saying 3 bonds away. It can hear E and it can hear C, right? 1, 2, 3. 1, 2, 3. So it hears 2 different songs, right? So D hears C and E. So what's C going to do to D? Turn into a doublet because of C. And then what's E going to do to D? Doublet because of E. Very good. what's E gonna be? So E can hear F and it can hear D, right? So what's D gonna turn E into? A triplet because of D. And then what's F gonna turn E into? The 7 is the heptet. Triplet of heptets. And that's because of F. And then finally, F for 6 whole hydrogens is going to be what? Easiest one on the whole board. F was, who does F here? Just E. So F is going to be doublet. Doublet because of E. Doublet because of E. F only hears E. And there's only one E. So 1 plus 1 is 2. Doublet because of E for F. So take a look at a mass spec kind of question. So we have a molecule like this. And the question I have is, what are 2 likely cationic fragments? So it's another way of asking is, which bonds will break to make a really likely cation? Which bonds would break to make a really likely cation? So I'm going to go ahead and number this for you arbitrarily to help us talk through this. So there I've numbered a 7 carbon piece. So I want to give 2 different scenarios. 2 different scenarios. What are 2 likely cation fragments and what bonds would break to make those? All right, we've discussed it. We've decided if we broke between C3 and C5, that would be a good spot. And then we could have a fragment with a plus charge on carbon 3. And that would be really good because that will be a tertiary carbocation. So that'd be a pretty likely fragment. Another scenario we came up with was between C3 and C4. C3 and C4 in the blue. We could have also done 3 and 1 or 3 and 2. They're all these methyls, 1, 2, 1, and 4 are all the same, so it doesn't matter which one we pick. But this again results in a different fragment, but a fragment with a plus charge on a tertiary carbon nonetheless. So that'd be a very stable cationic fragment. Right, so all this is asking us is basically, do you understand carbocation stability? Which bond do you want to break to make a really stable carbocation? So tertiary is good, benzylic is better, and allylic, right? Allylic is good, benzylic is best. Tertiary is good too, right? Think about those, remember those ways to stabilize carbocations. Yes.